Hello, my name is Andy Katz. I'm a product manager with AWS, and today I'm going to talk to you about serverless orchestration of workflows with AWS step functions. Application development is changing. We're moving from applications that were monolithic and the enterprises organized around the application to applications that organize themselves around the enterprise. And what that means is we move from monolithic applications to microservice-based applications, where applications may represent different departments like finance or manufacturing. But even within that, we can go finer grained by looking at functions within those departments, things like sales and the different people in sales. And our applications are starting to reflect that as we move from monoliths to microservices to functions. So when we're working with functions, how do we turn functions into apps? You may want to sequence your functions. So you may want a function run first, and then a second function follow after the first one runs. You may want to run two functions in parallel, and then when both are done, run a third. You may, for example, want to select what function comes next based on the output of the first function. So if the answer is A, go to the left. If the answer is B, then go to the right. You may want your functions to retry upon failure, and depending on the kind of failure, retry in different ways. Or you may want to implement a try, catch, finally pattern. Try this. If you get an exception, catch it, do something else. But if all else fails, finally do this thing. And in some cases, you have code that needs to run for hours. Lambda functions are very, very useful, but they do run only for up to 5 minutes. So how do you put together an application that needs to span more than 5 minutes? So you have options. One option is to think about coordination by chaining Lambda functions. One Lambda calls another, and so on and so forth. And this works, but the challenge, of course, is what happens when a Lambda function fails. That can happen from time to time. There may be an error in your code. The chain breaks and the application collapses. So you need to put in mechanisms to keep track of this. So perhaps you coordinate by database. Every Lambda function is stateless, and they look for their input, and then they record their output in the database, and the next Lambda function comes along, looks it up, gets the information, puts it back. And this can work. But again, on a relational database, this may not scale to the level of your application, and it's a lot of overhead. Maybe using a queue is easier. It certainly solves the problem of scaling. And so with queues, you can get to much greater size. But again, you need to handle all the retry mechanisms and all the coordination between the functions yourself. So what you'd really like to do is deliver a set of must-haves to your application. You'd like to be able to scale out. You'd also like to keep track of state between functions so that if a function goes down, you can continue from where you were and not have to start over at the beginning. You'd like a way to easily handle errors and timeouts of your functions in your application, calling APIs. Ultimately, you'd like this to be easy to build and operate, not just building it, but actually using it. And finally, you'd like to know what's going on in your application. And in a serverless environment, this can be hard. What you'd like is an audit trail that tells you what happened. Hence, we introduced AWS step functions. This is a service from AWS that's designed to make it easy to coordinate these components in your distributed applications with visual workflows. By using step functions, we hope to make you more productive, more agile, and more resilient in your applications. By productivity, we mean it's easy to connect and coordinate different distributed components of your applications to put together applications quickly. By agility, we mean you can find out what's going wrong faster and solve that problem sooner, but also evolve and adapt your applications over time more quickly. And finally, delivers the resilience you've come to expect from AWS by managing the operations as a service with nothing for you to worry about in terms of scaling, and high availability at scale and under different failure conditions of your microservices. So how does this work? So the application lifecycle in step functions has three basic pieces. You define your workflow in JSON in a declarative language we call Amazon States language. With that, the console can visualize your workflow. What you see in the center here is actually a visualization of a JSON document like on the left. And then finally, we use that graph in the console to let you monitor individual executions. So you can know what's going on in your workflow at any point in time during the execution or after it's concluded. So we take a look at each of these things in step. First, we'll look at defining the state machine. What you see on the left is the JSON that generates the state machine you see on the right. In this case, it's very simple. It's a hello world single state machine. You can see you can put comments in the JSON so you can annotate your code. You simply specify, where do I start? In this case, at hello world. And then you define each state. In this case, one state, a hello world state. And then you say the end is true. And this generates the graph on the right. Now, we'll talk today a lot about individual state machines, but what we're really talking about is state machine executions. And by this, step function supports execution of individual state machines or concurrent executions of the same state machine or collection of state machines up to 1 million concurrent executions in the system. And these can be long-running executions, so they can start and be open for up to 1 year. So you can run short, temporary things that last a few seconds up to workflows that last up to 1 year. In the console, you can monitor your executions. There's a lot of information you get from the console, and we'll show you more detail in a demo later on, but essentially everything you get on the console is also available programmatically through the API with one exception, and that is the graph itself. The graph is unique to the console, but all the other information I'm about to talk about is also accessible through the API. If you look in the upper right, you'll see details about your execution. We give you information about whether it's running, whether it succeeded or failed, give you the ARN of the execution itself and the state machine that it came from, when it started, when it finished. And you can click on the input and output tabs to see the input JSON you gave the state machine and the output that it generated. You can also look below and see where it says step details. You can click that and open up a similar set of tabs that gives you information about individual steps, the input to each step, and the output from each step. And you can step through them by clicking on the steps in your state machine graph on the left. Now on the left side, what you see is the graph itself and a tab that says code. So you can toggle back and forth between the state machine itself and the code, so you can see, for example, what retry policy did you set for a task state, or other design choices you may have made about the state machine that you don't recall at the time of execution. Also, when looking at the graph, you can see it's color-coded. Work in progress is blue, successful states turn green, states fail turn red, so you can easily spot by inspection what went wrong, and any states you don't pass through stay white. And finally, at the bottom, what you see is the full audit trail of the execution, step by step, not just the state transitions, which are the arcs in the graph, but the steps that were executed by step functions in each state. And they come with a timestamp, and you can open it up and see the input and output of each of those stages. So you get a lot of information from the console. And again, with the exception of the graph, everything can also be called by your code from the API. So using the API, there are 5 basic calls. You can create state machines or register activity workers that are a type of state in the state machine. You can start executions. You can stop executions. You can list all state machines, all executions, and all activities that the system is aware of. Or you can describe individual state machines, individual executions, and individual activities. And what you see in the console is essentially using these calls to get that information and format them for you. So building your state machines, we build them out of 7 state types. The most common is a task state. Task states are what does work in your workflow. We also have choice states to add branching logic. We have parallel states to let you fork and join data across different tasks. We have wait state to put in timers. We have fail and success states to stop executions under your terms and call them success or failure. We have a pass state, which lets you pass input to output. And this is useful for mocking up things like task states before you've integrated your resources. But it can also be used to transform the state payload from one step to the next, for example, reversing the order of 2 values. With these 7 state types, you can build a lot of different things. This is an example of a photo processing workflow, where what you see on the left is you take a picture, and you may want to tag what you see in the image using something like Amazon recognition, but also at the same time make a thumbnail. The workflow on the left is represented by the state machine on the right. This state machine is made up of task states, choice states, fail states, and parallel states. And what you see is it first extracts metadata about the image. It says if it's an image type I recognize, I can go forward and process using the path on the left. And if it's an image type I can't work with, I fail the execution, which is the path that goes on the right. If I can process the image, I'm going down the left branch now, I store that image metadata, store the image and its metadata on S3, and then in parallel, I can invoke Amazon recognition to identify the features of the image, like the mountains, the people, and the snow, add those tags to the image, but in parallel, also make a thumbnail and store that in S3, and then exit. So let's look at each of these tasks, these states in more depth. So task states, pull or push. By push, we typically call a lambda function. So in a task state that has a lambda arn, it will push the state information to the lambda function in the form of a JSON document and wait for the lambda function to return a result. So it's a round trip that's managed for you by step functions. On the other hand, you may have compute resources that are on premises or in EC2 or ECS Or you have a need for a longer running compute job than 5 minutes. In this case, you can actually also poll using what's called an activity task state. In this case, instead of giving a Lambda function ARN, you give it an ARN of a activity which is registered with step functions in advance, and it's poll based. What this means is that your compute instance long poll step functions, much like polling SQS for a message, and says, do you have any work for me? And it identifies the kind of work it knows how to do by presenting the ARN that you registered with step functions. If step functions has a state machine, in that state, it will dispatch the work to that worker and wait for it to return a result by sending an API call with the result saying I succeeded or failed in my mission, and giving a token back that identifies which state machine that payload came from. And so again, push or pull from step functions. Push supports Lambda functions, pull for all other compute resources. So task states ultimately dispatch work, and how they dispatch work again is through an ARN. So you see the format of a task state in this slide. On the left side you see the JSON. We specify the type task, we give it a resource, in this case the ARN of a Lambda function, and the state machine on the right, which is a hello world example again, will in this case dispatch a call to a Lambda function and wait for the result to come back. Now sometimes things go wrong, and so you can retry. And so in the same task state, we can put a retry policy that says if I get an error back, and we have two types of errors, errors that are generated by the service and errors that you generate yourself, we can retry. And we can specify how many times to retry, how long to wait between attempts, and how many attempts to make. And so what you see here is 1 second intervals with an exponential backoff rate of 2 seconds per retry, and a maximum number of retries of 2. So this will retry twice before failing the execution. You can also introduce catch clauses into your task states. So in this case, depending on the exception you get, you can go to different states. So not just retry, but go somewhere else in your state machine. So in this case, a custom error, you can return an exception from your Lambda function or from your EC2 instance or your on-prem server. And based on the error you send, you can go to different states. Or we have a set of reserved errors. These begin with the prefix states.star. In this example, states.taskFailed. And those can also be captured and send you down different branches in your state machine. Now, when you make the hello world example with catch states, it looks different. So when you look at your hello world state machine with catch states in it, now the graph will show the fallback error conditions. In this case, we have a custom error fallback, a reserve type fallback, and a catch-all fallback, where you go if no other exceptions match. Now, when you want to handle a custom error, how do you do it? So this is an example using Python. What you see above is a snippet of Python code showing how we raise an exception in Python and what it looks like in the state machine itself. So in the bottom you see the catch clause where the error equals account already exists exception. You can see the same phrase above in the Python snippet, and this is the connection for Python. This is language specific. We've written in the documentation as well as a blog on how to use this for Python, Java, Node, and C#. And as Lambda adds other runtimes, we will update the exception handling to support those languages as well. Choice states add branching logic. So in this case, you specify the state type choice, and the choices are a set of pairwise comparators. So we compare a variable from the input to the state. In this case, the JSON path is $.foo, and we ask, does numeric equal 1? If so, go to that first match state. If not, go to the next comparator. In this case, comparators equal 2. If yes, go to that match state. If not, go to the next comparator. You can compare numerics, strings, timestamps, and booleans in your choice state, and you can construct them with ands, nots, and ors in the function as well to build fairly complex branching logic in your state machines as needed. Parallel states let you fork and join processes, and this is a specific kind of parallel state. In this case, what's happening is it clones the data across multiple branches, and you do different things to the same data. This is different than doing the same thing to different elements of data in, say, an array. So in this case, it's the first, not the second. Again, you specify the type parallel, and you say where to go next when you're done with the parallel state, and then inside the parallel state, you're essentially specifying small state machines. What state to start at for each branch, what states to pass through in each branch, and then when you're done with that branch. And you can construct 1, 2, 3, 4, 5 parallel states and beyond. Your constraint is by the total number of steps an individual execution can have, That's maxes out at 25,000 per execution. In practice, that leads to 1,000 to 2,000 states in your overall state machine that you pass through during an execution. So quite a lot of parallelism is possible. Wait states give you timers. There are 4 flavors. So you specify the type is a wait state, and then you can use 2 syntaxes. One is to say how many to wait in seconds. The other option is to say wait for a timestamp to emerge. The variation on each of these is using a JSON path from your input to specify how long to wait or what timestamp to wait for, which allows you to put in things like timing loops, where you can change how long you wait in each pass of the loop by updating that variable in the JSON path. Everything we've shown so far is available as blueprints in the console, so you can explore each of these patterns by clicking on a blueprint in the console, seeing what the code looks like, and making modifications and executing those state machines yourself. So what do people do with step functions? A lot of use cases. Workflow and order management is a common use case. Managing batch processing is another case. It's simple enough that you could think about replacing shell scripts with step function state machines, but it's also robust enough to replace enterprise application workflows at scale, and then also data gathering and processing. For example, where using a Spark job is too extensive, you might do something simple with step functions. So one pattern, for example, is synchronizing S3 buckets. In this case, you imagine you're running a website and you want to transition one set of resources to another. So you have a dev and a prod S3 bucket. This is a state machine that will essentially look at the source bucket and compare it to the destination bucket. Anything that's in the source bucket that's not in the destination bucket will get transferred. Anything that's in the destination bucket that's not in the source bucket will get deleted. This is a state machine that we have available on GitHub as a reference architecture. We also have a blog that we recently published, so you can look and experiment with this state machine and see how it works with your own S3 resources. Another example is data processing of big jobs. Step functions is a very good way to coordinate dependent sequences using AWS Batch or Amazon EMR. This is an example also published using genomics, where you've got a sequence of batch processes that you want to run in a particular order. At the heart of this is a simple state machine that submits a job to AWS Batch, checks the job status, and then uses a choice state and says if the job is still pending, wait, check again, and if the job is finished, go on to the next step. And by using this unit cell, you can see the graph on the right is a state machine that will actually transition data through 3 different steps going down the left branch, and then in parallel running a QC process in a batch job on the right. And again, this is written up in a blog, and we have a reference architecture available as well on GitHub. You can also schedule jobs using CloudWatch events. So you can create a rule with CloudWatch events that has a schedule with either a fixed rate or a cron expression to start state machines on a schedule. CloudWatch events also allows you to respond to events in your AWS resources. So you can build serverless solutions to managing your AWS resources. This is an example we recently published in GitHub on EBS snapshot management. And what this job does is when you take an EBS snapshot, it sends an event to CloudWatch events that triggers the start of a state machine, which will tag that snapshot, make a copy to a disaster recovery region, then check to see how many out-of-date snapshots are in that in your region, and delete the old ones. And then the same thing will happen in the disaster recovery region. When the snapshot backup is copied over, it will trigger a second state machine, again through CloudWatch events, that tags the DR copy, counts how many old DR copies you have, deletes the ones that are out of date, and then sends notifications that the job is complete. And again, it makes sure that the new copy is successfully in place and tagged before it starts deleting old copies. So you save money by not having out-of-date storage, but you also ensure that your new copies are safe and sound before you start deleting old copies. Another example is human approval tasks. Many times you need something like a vacation request approved. This is a pattern on how to do that in a serverless manner using Lambda functions and activity tasks as a way of passing a token through a request. So in this case, a Lambda function on a schedule pulls step functions that goes into an activity task state. Step function sends that Lambda function a token saying, I need this work done, in this case a vacation approval. It might give the Lambda function the email address of the person who needs to make the authorization and the employee that's affected. That Lambda function uses Amazon SES to craft an email that contains two links, approval and denial of the vacation request, and sends an email to the approving manager. The manager looks at the email and can click the link of approval or denial, and that can happen at any point in time after receiving that email, up weeks, months, or even a year, and then goes through Amazon API Gateway to call back Step Functions API with task success or task failure. So this is an example of how to do it for human approval tasks, but the broader pattern here is that you can pull a token from Step Functions, pass that token between microservices, and Step Functions can supervise the entire process from start to finish. That activity task state can include timeouts and retries, for example. But essentially, it can wait until the entire process is done, and the only price you pay for failure is starting the process over again from the beginning. At the heart of Step Functions is state passing through a state machine. State payload is the oxygen or the blood of the system. In this case, every state has an input and an output, but there are a lot of things you can do with the input and output in between. We have filters called input path and output path, and we have a pointer called result path that lets you process JSON and place results into JSON. So let's look at how each of these things work in turn. Input processing. Suppose I have raw input, two key value pairs, title and numbers. If I specify the input path as being just numbers, then the task input will simply be 3 and 4, and it will drop the string from the title. If you don't give an input path, then Step Functions will pass the full JSON block to the input of your Lambda function or your activity worker or any other state as is. If the input path is null, then states will send an empty object to that worker. That could be useful, for example, if all you want to do is send a notification. Input path, if it generates plural output, then states will put it in a JSON array and then send it to the resource. Result placement is done with result path. So in this case, suppose our input is two key value pairs, titles and numbers. Again, we said just give us numbers in the input path. But in the result path now, we say put the result in a value called sum. Now the output appends sum to the input. In this case, we get back titles and numbers, and now the sum, 3 plus 4 equals 7. Output processing is like input processing, but in this case, instead of prepending information in front of the resource like a task state, it filters the information that is passed to the next state in the state machine. So in this case, again, input path limits us to numbers, result path places the sum, and now we say the output path, all we want is the title and the sum, and we leave behind numbers. And so you see the output here, we dropped the numbers key value pair from the output of the state machine. Similar considerations apply. So for result paths, again, this is the pointer. This is different than input and output paths. If you don't provide a result path, we discard the input and we give you the raw output. If the result path is null, then the input becomes the output. It just passes through as is. We do not allow plural output from the result path. So the result path is placed in a single value. If you have multiple results, they get put in as a string. So now we can take a quick look at a demo of how this all works in action. So this is an example of Step Functions dashboard when you log into the console. So one of the first things we can do is go to the dashboard and create a state machine by clicking the button here in the upper right. And we can say, give it a name. We might say, hello AWS. We can pick a blueprint. In this case, we'll pick the Hello World blueprint. What you can see down below is we see the JSON on the left and the graph is generated on the right. If I pick a different blueprint, I'll get different code, I'll get a different graph. In this case, for simplicity, we'll stick with Hello World. We click this blue button, Create State Machine. And it'll offer you a default role, or if you don't have one, you can create one. And there are instructions in the documentation if you have difficulty getting an IAM role for your state machine executions. State machine is created, and we can give it a new execution. In this case, the input's not important. We can make it whatever we like. We give an execution name. And then run it. And so in this case, the state turned green right away. You can see here's that Hello World code. If we look here on the right, we can see the ARN of the state machine we created. We can see the execution ID. If I look at the input, we said We change the comment field. In this case, the past state replaces that with hello world, and that's the output of our state machine. We also look in the step details, click on a state in the graph, see there were no exceptions, see the input and see the output again. And then down below, we can see individual states, the input, the roles that were used, and literally audit every single step in the state machine. This is interesting, but let's look at a more elaborate example, in this case, an order processing example. So here's an example of potentially an order process from two regions, say US and Europe. And we're reading orders off of a Kinesis database. So we want to fetch an order, identify the region. If it's a region we serve, create the order. If we have some errors, handle them. Otherwise, process the order and move on. So let's run one of these. Say new execution. In this case, I have to put in special information. I'll say that we're ordering from the EU. We're willing to wait 4 seconds for that order, and we'll randomize it, and we'll see whether we succeed or fail. So in this case, we start the Lambda function fetches an order. Specifies the EU, creates the order successfully, processes the order, and exits. You can see our input. We gave it what region, how long to wait. In this case, our output. How long did we wait? We waited 1.1 seconds, and we have some information about how the order is being shipped because the state machine changed state as we went. We can see where these changed by looking at step details. In this case, looking at the region choice, we can see the input and the output are the same. When we go to create the order, we see the input and the output are changed. What happens? The create order EU, we could look at our code. If we scroll down, we can see create order EU is actually a task state calling Lambda function. That Lambda function is now changing the values. In this case, we can imagine that it's making a call to a database. And in reality, this demo we made simple. We're using random number generator with a timer, but this is a way you can find out what's going on. Now, what you'll also notice is we have a timeout. We're willing to wait 2 seconds. In this case, we waited 1, so we were within the timeout. We could set this thing for failure. So for example, we could say, make sure it fails by running this execution one more time. Inserting our JSON. This time, let's make the wait time 20 seconds. Now it's likely to fail. Our timeout was 2 seconds. Get to the create order. It'll retry, and it should time out. There we go. It claimed a database error and said no order possible because we actually forced the database to fail. What you see when we look at the audit log is we see a series of timeout, 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 and again we said we'll let it try 2 more times before declaring failure, and so it did. In this case, it went to the database error, which was a catch clause, and then fails the execution by saying no order is possible. So this is an example of how state machines can handle errors, recover gracefully automatically for exceptions you're aware of, and only fail when you have intended catastrophic errors that you didn't anticipate. So that concludes our demo. So let's talk about integration. So Step Functions works with a lot of other AWS services. For example, you can automate deployments of state machines and their associated resources using AWS CloudFormation. We also send API calls to CloudTrail, and we send metrics and graphs to Amazon CloudWatch. You can see how many executions you've started, how long they're lasting, how many jobs you may have pending in an activity queue, etc. We also have integration of CloudWatch events. As we mentioned, you can start state machines on a schedule or start state machines in response to events. And we're also integrated with API Gateway, which will allow you to send API calls through API Gateway either to start state machines or to do things like respond to open activity task states. So common patterns. You can use choice states for looping. So if you need to have a loop to wait, you can do so. If you need to restart a process and go up 5 steps, you can do that. Pass states around to inject values into states, so you can add information as you go or mock out resources before you've integrated them into your state machine. You can use retries to manage API uncertainty. So where you have a Lambda function that calls an API that's unavailable, you can set a retry policy that backs off exponentially, and you can have retries 2, 3, 5, 10, whatever is appropriate for your use case. We recommend that you think about using step functions wherever a shell script is making you nervous. Shell scripts have this nasty habit of outliving their intended 1-week lifetime and turning themselves into apps. So why not start with something like step functions, which naturally lets you evolve it into an application. Feel free to use parallelization wherever possible and appropriate. If you can't do something with the input and output paths, it's Not a big deal to write a Lambda function to do further JSON processing. They're short and simple, and it's a good pattern. And finally, when you're building up your state machines, build them in pieces. Don't start with the whole thing at once. Build them out from little building blocks as you go, like we saw in that genomics example. Finally, when you're thinking about building with step functions, don't use try-catch too much at the Lambda level. Think about moving that into the state machine. This makes your Lambda functions more reusable, much simpler, and lets you separate the undifferentiated logic of the application from the actual business logic in your Lambda functions, which makes your app of interest to you. If you're calling a Lambda function over a Lambda function, you probably should be asking yourself, can I do this with step functions with more effort, with less effort, and more resilience? Do think about decomposing some of your larger applications or your larger scripts into a state machine and a set of Lambda functions. Think about using SAM, Service Application Model, with CloudFormation to manage many small Lambda functions. And do think about automation of your state machine builds, as that will make it easier. Thank you for your time. If you'd like to see more resources, you can visit our console at amazon.com/stepfunctions, or I encourage you to visit the Getting Started page from our landing page, which includes all the examples I showed you, both reference architectures and blogs and other information about step functions to help you get started successfully. So now we'll answer some of the questions that have come in during the course of this webinar. So first question comes from Raj, who asks, is step functions only for Lambda functions? The answer to that question is no. While step functions is very good for developing serverless applications with Lambda functions and other serverless services from AWS, such as S3 or Dynamo, step functions can also work with any compute resource that can reach its API over the internet. So that means EC2 instances, ECS containers, on-prem servers, even a mobile phone. If you can reach step functions through the internet, you can request for work. So while it's got a very strong use case in the serverless landscape, it's good for microservices in general. Question from Mike says, I see Python as a supported language. What about other languages such as JavaScript or PHP? So step functions is language agnostic. Activity workers can be written in any language of your choosing. We have support in the AWS SDK for many common languages, and specifically Lambda today supports 4 languages, and step functions are compatible with all 4. Those are Python, Java, Node, and C#. But certainly you can look for the AWS SDK for support for step functions of the language of your choosing. Question from Mark. Does the SAM template support step functions as a resource type? Yes, you can include step functions in the form of a YAML string block or a JSON string block or a stringified JSON in your SAM templates. Any CloudFormation statements that you put in CloudFormation can also be put in a SAM template. That said, we are also actively working on improving the SAM experience with step functions, so expect more improvements in the future. Question from Kang. Will step functions replace simple workflow in the near future? The simple answer to that is no. We will continue to develop and support simple workflow, and if it works well for you, we encourage you to keep on using it in absolute confidence. That said, we do hear from a lot of our customers that step functions does provide an easier and more productive approach for many of them. So our recommendation is that you use step functions for your new applications unless you need specific functionality from simple workflow that's not available in step functions today. These would be things, for example, like launching a child workflow that returns a result to the parent workflow, or if you need signals. Then you might consider using simple workflow. But for most applications, you'll get all the benefits of simple workflow with increased productivity using step functions. Question from Ishmael. Can a state machine be mapped to an S3 notification event? The answer is yes. Using CloudWatch events, you can actually start step function state machines in response to events such as S3 notifications at the bucket or object level. If you want to do bucket level eventing, you can do that directly with CloudWatch events. Object level, you can turn that on through CloudTrail, sending object level notifications to CloudWatch events. Question from Kim. Is this like BPL or BPMN? Not quite. Amazon States language, which is the declarative JSON we use to define workflows is really intended for developers, and BPL and BPMN are much more designed for business level workflows. You certainly can map BPMN onto ASL, but really this is designed more for people developing applications in the cloud. Question from Joseph. Doesn't Lambda retry 3 times automatically? And how is this different from step functions retrying Lambda functions? What is the maximum wait time supported? So Lambda retries for your asynchronous invocations that are coming from event triggers like Dynamo or S3, and has a default retry policy of 2 times before putting that function in a dead letter queue. And synchronous invocations do not have a retry. If a Lambda function sends an error, then the calling service gets a 400 error back from Lambda and must handle retries itself. Step functions, when it calls Lambda for you, makes synchronous calls and lets you, as we saw, define those number of retries. So in this case, you can specify 1, 2, 3, 4, 5, 50 retries if you choose, as well as how long to wait between retries and even different policies of retries depending on the error you get back from that Lambda function. So a lot more flexibility using step functions for your retry. But again, it's really going to depend on your use case, but that's the difference. Question from Janet. Can you specify your own error messages? The answer is yes. So function error handling for Lambda functions, you can also do something similar with activity task states. You can find more about this looking at our Getting Started page as well as in our documentation. Question from Mohammed. For any given step function transition, how long are logs of success, failure, etc. kept? So that history that step functions emits is stored in the service for 90 days after the close of an execution. So after an execution ends, we store it, and you can access that by using an API called getExecutionHistory. Again, if the execution lasts a full year, you have that log available during the execution up to the last step it's in, plus 90 days after that execution closes or fails, whichever comes first. Question from James. When would I use step functions versus batch? Can this be invoked at a scheduled time, basically using as a batch job? So yes, AWS Batch is a very good service for batch processing, and as we saw, you can use step functions plus batch in a very nice combination for managing batch dependencies. And with CLOUDWATCH events, you can schedule step functions to run your batch jobs on schedules to have batch jobs. So yes, yes you can is the basic answer. We recommend looking at both batch and step functions in tandem for your specific needs. So that's all the questions we have time for today. Thank you so much for your interest, and stay tuned for more information from AWS Step Functions in the coming year.